All right, let's look at proving functions are differentiable at given points. And in this lesson, I will be using this sheet right here. If you want to go to that bit.ly link and print that sheet to follow along, you can. If you are one of my students, I will probably give you that sheet in class so you wouldn't have to print it. So let's talk about the relationship between differentiability and continuity. And this is something that I hope you already know. But if a function is differentiable at x equals c, then that function must be continuous at x equals c. And the contrapositive of that statement, which means you flip the whole thing around and insert a couple of knots, that is also a true statement. And so we will take advantage of this fact. If f of x is not continuous, then f of x is not differentiable. And that's actually going to be our first step in proving that a function is or is not differentiable at a given point. So our game plan, first we want to establish that your function is continuous because, again, if the function is not continuous at the point in question, it will automatically be not differentiable. But do remember that proving continuity must be done through limits. We're going to show that the limit as x approaches c of f of x does indeed equal f of c. And remember that you do frequently need to look at this limit from left and right sides of c separately. Then, if the function is continuous, you want to show that it is differentiable by eliminating the possibility of a cusp or a corner. And we do that by showing that there is no abrupt change in slope. So if you think about a continuous function that does have a cusp, at that cusp, you have a very immediate change in slope. In this example I just drew, we have something positive, and immediately at a point, it is a slope that is negative. It's not a gradual change. For a function to be differentiable, the function must be smooth and continuous. And if you look at a differentiable function at any point, if you look just to the left and just to the right, the function has the same slope, and that's what eliminates the possibility of a cusp. And we will do that by, again, looking at limits, but we are going to show that the limit of the derivative, the slope, on left and right sides of the point in question are equal. So we do the limit of the derivative on left and right sides if the function is continuous, and if those are equal, there should be an equals m in here. If those are equal and they do equal a real number, then you have a differentiable function. So there are the basic notes, your game plan for showing differentiability. Let's do a few examples. So here we have this piecewise function x squared on the left side of 3, 6x minus 9 on the right side of 3, where you want to show know if this function is differentiable at x equals 3. So first we're going to show continuity, and the game plan for continuity is you want to show that the limit as x approaches 3, and because left and right sides are represented by different equations, I'm going to have to look at 3 from the left. I will have to look at 3 from the right, and that is not enough. You also must, in writing, show that f of 3 is equal to the same thing. So up here, the left side of 3 is x squared, so 3 squared is 9. The right side of 3 is 6 times x minus 9, so 6 times 3 minus 9 is also 9. So now I know that the limit exists, and f of 3, x equals 3 on that bottom piece, so that is also 6 times 3 minus 9, that is 9 as well. So now I know that f is continuous. F is indeed continuous at x equals 3. The question is now, is there a cusp or a corner? We know we have the continuity. Now, is f smooth? And to show the smoothness of f, we need its derivative. And the derivative of a piecewise function, you will simply differentiate both pieces separately. So my derivative would be 2x for x is less than 3. My derivative will be 6 for x is greater than or equal to 3. And we will now look at that derivative on left and right sides of 3. Limit as x approaches 3 from the left of the derivative. And I want to know if that is indeed equal to the limit as x approaches 3 from the right of the derivative. And as we look at left and right sides, you will see that those are equal. They both equal 6. Therefore, f is differentiable. And I'm kind of lazy. I just write diffable. F is differentiable at x equals 3. The function was continuous, and we showed that it was smooth. And you have to satisfy both of those to show differentiability. Now let's look at another one. So number 2, x squared plus 1 for x is less than or equal to 3, 5x minus 3 for x is greater than 3. And so we want to first show that the function is continuous. So I'm going to look at the left and right sides of 3, and I forgot to do f of 3 also. Let me put that down here. And then I'll compare those to f of 3. So limit as x approaches 3 from the left, that's my top part. So 3 squared plus 1 is 10. X approaches 3 from the right would be 5 times 3 minus 3, which is 12. And since those are not the same, I know there is a discontinuity. I don't care about f of 3. I now know that f is not continuous at x equals 3. Therefore, f is not differentiable at x equals 3. And that this part up here I have in green does not matter. I don't care if f is smooth or not. Actually, it won't be smooth. It's not even continuous. So we don't care. And this is kind of a nice question here because we kind of could stop early. We didn't have to go through that second step of showing the smoothness of the function. All right, so let's look at another one, number 3. And I'm going to go a little bit quick on this one because it's pretty similar to number 1 and number 2. We want to first show that the function is continuous, and we do that by looking at the left and right limits. And so here's what happens when you do the left and right limits. You get 1 for the left side, you get 1 for the right side. F of 2 is 1. So I know that f is continuous at x equals 2. Now we want to determine if this function is smooth at x equals 2. And to do that, we will need the derivative. And so let me get this out of the way. Here's my derivative. And when I do the limits to determine the smoothness at x equals 2, we can see that the derivative is 2 on the left side of x equals 2. It is negative 1 on the right side of x equals negative 2. Those are not equal. That is not a smooth transition through the point of 2. And if you looked at it graphically, you could actually do this one kind of quickly in your head because this top piece is a line with a slope of 2. So we're coming in at 2 with a steep slope of 2. And then at 3, we very abruptly change to a slope of negative 1. And we will have a corner, if you want to think of it graphically. But on paper, if you are proving continuity and differentiability, you do want to go through the limit explanation. And so I have one more example. And this one's going to be a bit of a booger because of the way it is asked. We're again showing differentiability, but you are told explicitly to use the definition of a derivative. And when you see that phrase, that is a cue that they are wanting you to actually use limits in the derivative, not the derivative shortcuts. So the two definitions of a derivative that you need to be familiar with are here. F prime of a is the limit as x approaches a, f of x minus f of a over x minus a. And then f prime of a is the limit as h approaches 0 of f of a plus h minus f of a over h. I personally prefer the one on the left, especially if I have a point in question. So here, I'm trying to show differentiability at x equals 2. So I'm going to replace all of my a's with 2. So f of x minus f of 2 over x minus 2 as x approaches 2. And over here, f prime of 2 would be f of 2 plus h minus f of 2 over h. So I'm going to replace those a's with a 2. But I only need to go through all of that if the function is continuous. And I just noticed the typo here. Use the definition of a derivative to show that the function below is differentiability. So I need to adjust that. That is differentiable. And actually, the way this is worded, it's not a question of whether or not this is differentiable. They tell you it's differentiable. We just have to show that this is differentiable. So I actually will end up using these limits. But first, we're going to show continuity. And because we've done that a few times, I'm just going to show you that this function is continuous. You look at the limit from the left, the limit from the right. Don't forget to include f of 2. Those are all the same. Now we have to show that this function is smooth. And we have to show that through limits. So we're going to show smooth. Show this function is smooth through limits. And I'm going to go with the one on the left. Now, if I'm going to do this, I've got to look at x equals 2 from both sides separately. So actually, I'm going to have to do this limit twice. So on the left side, I'm going to do the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2, which is going to be the limit. And I'm going to substitute my functions in here. F of x is x minus 1. F of 2 down here is 1 all over x minus 2. And then for the right side, we're going to do the limit as x approaches 2 from the right. F of x minus f of 2 over x minus 2. The right side is x minus 1 squared. F of 2 is 1 all over x minus 2. And I'm going to pause the recording and work this out really quick. And then when I come back here in just a second, you will see that these are indeed equal. All right, so I just finished working this out and realized I did a terrible job of writing this question, typos aside. It turns out that the left side limit showed that the slope is 1 on the left side, and when I worked out the right side, I expanded that numerator and factored out an x. When I canceled that, the right side actually has a slope of 2. So my left and right sides actually did not have the same slope, and therefore this function is actually not differentiable. Function was continuous, it is not differentiable. So a little typo here, not a typo, just a poorly worded question. I guess I could salvage this simply by saying use the definition of the derivative to determine if, there we go, determine if the function is differentiable at x equals 2. So with that slight adjustment, I have now shown that f is not differentiable. And if it was differentiable, I would have gotten the same slope here on the left and right sides. So slight mistake, although the execution and the thing to be learned from this does not change. F is not differentiable at x equals 2. So there we go. So there's proving differentiability using both shortcuts and with the limit approach, and hopefully that made some sense for you.